quadratic number fields. Before that, I want to do a really quick recap on number fields. I will just recap or refresh the things that I need for this talk, but I assume most of you will have had some number theory course in the past. So let me just start by saying that we are working with a quadratic number field Q with the root of d added, where d is an integer different from 0 or 1, which is square free. So this is a quadratic number field. Yeah, you can show that any quadratic number field is this form. And in this quadratic number field, I need two important maps, which are the norm map. So the norm element, which can be written as a plus b squared of d, is defined as a squared minus b squared d. And I need the trace map of an element, which is equal to 2a. I hope most of you have seen this some time in the past, but these are just things I need. Okay, and then a really important ring for a quadratic number field is the ring of algebraic integers, which we denote by OK. This is the integral closure of Z inside K, the quadratic number field. Okay, so this is a really important ring. Most of you will have encountered this when studying Dedekind domains, because this is a classical example of Dedekind domain. And inside this ring, we have subrings, and we will take a specific type of subring called an order. So an order O of K is a subring of OK, such that the fraction field O is equal to K. So OK also has this property, and then we take subrings, which we call orders, which also have the property that the fraction field is K. And these are really important because we will define a class group of an order. Most of you will have seen the class group of the general Dedekind domain. So we will define a class group of an order and then show a correspondence with binary quadratic forms. Okay, so now I want to specifically about a quadratic number field. I want to write down some facts which you can show about what such a quadratic number field looks like and how it is determined by its discriminant. So let's be a square free integer. Then the following things hold. If we have, depending on the residue modulo 4 of d, we have two cases. So if d is 1 mod 4, then we know that the ring of algebraic integers looks like z with 1 plus square root of d over 2 added. Okay, this might ring a bell for some of you, for most of you, I hope. And the discriminant of the field is equal to d itself. I refreshed on the handouts what the definition is of a discriminant specifically for a quadratic number field, but I just want you to remember that the discriminant, in the case of a quadratic number field, really determines what the field looks like. So for a discriminant, there is a unique quadratic number field, okay? And it also determines what the ring of algebraic integers looks like. And then in the case where d is 2 or 3 mod 4, then OK is of the form z with root of d added, but the discriminant not equal to 4d. Okay, so these are some characterizations of number fields and their integral closure inside K. And we also know what an order looks like. So if O is an order of K, then the following fact holds, then this is also called the order, but the order of O inside the bigger ring, OK, is finite. And we call this number F. We call this the conductor of the order, because the order is entirely determined by this specific number. The order actually looks like Z with F times omega K. Now, by omega K, I just mean the specific element we appended in either case. Okay? So an order is determined by its conductor. So I call this the order of conductor F. And the discriminant of this order is actually F squared times the discriminant of K. So these are important things I want you to remember. The discriminant determines the quadratic number field, and an order is determined by its conductor. So this is really nice. In another case, it's really explicitly computable, I guess. Okay, and then the important definition, it's in the title. What is a class group? So I hope most of you have already come across this concept. I also refreshed it in the handouts. So this is what I call a class group of an order. So what I mean is this set J is a set of invertible fractional ideals of O. I reminded you what a fractional ideal is. We have a multiplication on that, and this forms a group. Okay. Then we look at the subgroup of principal ideals of O. This forms a subgroup, and we can look at the quotients, which is what we call a class group of O. Okay. I hope most of you remember this vaguely. And then I need a stricter concept of the class group, specifically to show this correspondence, which is the narrow class group. This was also new to me before starting my thesis, but this is the same group J, but now we quotient out P plus of O, which are the principal ideals, which are generated by an element which has a positive norm, a strictly positive norm. Okay, this is also a subgroup because the norm is multiplicative. So if two elements have positive norm, their product will also have positive norm. And this forms a subgroup, and this is what we call the narrow class group of an order. Okay, I hope everybody is still following, because this was the quick recap I wanted to do on quadratic number fields. So I can now give you an introduction on binary quadratic forms.
So the narrow class group is the larger one?
No, this is a smaller subgroup. There are less elements which are positive norm, so we are dividing out less.
And therefore the program is bigger.
Yes, yeah, you're right. It's bigger, yeah. And yeah, maybe one thing I want to mention is if D is negative, so we have an imaginary quadratic field. Actually, every element has a positive norm. So the narrow class group for a negative D is actually the same as the normal class group. But you're right, it's bigger. Sorry, I got confused with
It's the cosets which are.
Yeah, the cosets are restricted. The class group is bigger.
Yeah, and can I be confused about something? So this order, so you say an order is a sampling whose fraction field is the fraction field of the of OK. So you take sort of the smallest one, or because OK is also an order of OK.
Yeah, OK is actually what is often called the maximal order. It's actually the order which has conductor 1. So it's the maximal one, and then you look at smaller conductors inside of, depending on just what I really want you to remember is that in the quadratic case, this is determined just by F.
But not all F give rise to an.
No, not necessarily. That's also important to notice. But that's a notion that I won't discuss today, but it's actually related to the theorem. Okay, so now I want to introduce you to something that was new to me this year as well. but which I really have turned to like. So a binary quadratic form, I will just put the definition. Binary quadratic form is a homogeneous polynomial of degree 2 which is in the quadratic part, in 2 variables, which is what the binary part refers to. So homogeneous polynomial degree 2 in 2 variables. So we can write it as from Q of xy, which you write simply with 3 coefficients a, b, and c. This is what a binary quadratic form looks like. It's not really difficult. And this is often abbreviated simply to the coefficients since they determine the quadratic form. Okay. Then Q is called integral if the coefficients are elements of Z. So the title mentions integral binary quadratic forms. This is what we will be referring to, but almost always this is abbreviated to binary quadratic forms or even quadratic forms, simply because of the context that it's clear that we are working over Z and that we are working with a binary quadratic form. So I will usually denote this by BQN, simply binary quadratic form, but I really mean an integral one. Okay? And then a form is called primitive if its coefficients are co-prime. Okay, those are the introductory definitions I want to give. And then, similar to how we have a discriminant for an order, there's also a notion of a discriminant for a binary quadratic form. And it's of course not a coincidence that they have the same name. So for a binary quadratic form A, C, the discriminant is defined as delta of Q, which means it is B squared minus 4AC. Okay, this might also ring a bell. Looks like the discriminant of a quadratic equation, and it's kind of related, of course. It's just homogeneous now. But the real reason this value is chosen is because any quadratic form can be written in a matrix form. So form with coefficients A, B, and C can be written as a matrix multiplication. Like this, with xy, yx, and then this matrix, which is over Q, which we write as NQ. So any quadratic form can just simply be written in this way. What we see is that the discriminant of Q is actually a multiple of this, the determinant of this matrix. Okay, this is an important fact. And the multiple 4 was chosen so that this is a whole number, and also so that the theory all lines up. So this is the correct definition, even though it might not be completely intuitive. Okay, so we have a discriminant, and now we want to look at a more specific set of binary quadratic forms, which are related to the theory of representing integers. So a lot of times problems in binary quadratic form theory are related to which integers can we represent if we fill in integers x and y, and which values can we compute or can we reach. And the discriminant actually has a really important role in this, because it determines which integers can be represented. So that's ABC. The binary quadratic form. Then, if the discriminant of Q is bigger than 0, then actually Q represents both positive and both negative integers. I mean strictly positive and strictly negative integers. But if the discriminant is strictly smaller than 0, we have two cases. Either Q represents only strictly positive integers, in the case that coefficient A is bigger than 0, and Q represents only negative integers if A is strictly smaller than 0. Now, I'll give a quick sketch on why this would hold. So, actually, the discriminant appears if we look at 4A times the form. If you write this out, you can actually decompose it. Let me check that I get this correct. And you can decompose it into a part in a difference of 2 squared. Except not entirely, we have the discriminant appearing here. So this is just an equality that holds. And you can see that if D is smaller than 0, this is some value bigger than 0. And depending on the sign of A, we represent solely positive or solely negative integers. But if D is bigger than 0, it's possible that both negative and positive integers are represented. Okay. The reason I mention this is because now we want to give a more specific definition of forms. We call a form. We call it indefinite if the discriminant is simply bigger than 0, so the first case. We call it positive definite if the discriminant is smaller than 0, but A is bigger than 0. And we call it negative definite in the final case. A is smaller than 0. So this is an important distinction I want to make. So in the case that the discriminant is positive, there's no clear distinction between what we call positive and negative definite forms. But in the negative discriminant case, there's a real clear characterization. Actually, these are the same thing, just with a minus sign in front of it. So that's why we make this distinction. Okay.
This is the same as saying that the matrix is positive definite or negative.
I think so, yeah. I think it's, yeah, it depends on the determinant, and yeah, it's really boils down to almost the same thing, I think. Yeah. Okay, let me. Okay, now the next step in getting to the correspondence, is imposing a kind of equivalence relation on these forms, similar to how we have an equivalence relation on the ideals of our class group. Okay, so what we do is we want some equivalence relation which preserves the discriminant of our form. So we take a matrix which has determinant 1. These are the 2 by 2 matrices which have determinant 1. And the reason we do this so we define an action of A as follows. I'm calling Q of this line, with A acting on it on the right. And we say that if we write it in the matrix form, it's actually multiplying with A and B transpose on both sides. And now, of course, the nice thing is, if you want to compute the discriminant of this new form, you see that the discriminant remains the same as we are multiplying the matrices with determinant 1. Okay, that's why I wrote this part. You can see that this has still the same discriminant. So we say that two forms are equivalent. Two forms Q and Q prime are equivalent. There exists some form, some matrix such that Q prime is Q with A acting on this. Okay, and then immediately you notice that if two forms are equivalent, then their discriminant remains the same. Okay, this is really nice. And now, if you look back at why I wrote this part, we have a characterization of positive, definite, or indefinite forms based on the discriminant. So a corollary of this part is that we can restrict our equivalence relation to positive, definite, or to indefinite forms. I'll just write that positive definiteness is preserved by the action of this. So this is also really nice. We can restrict even further. And then one final proposition, which I won't show here, but it's not that difficult to prove, is actually that primitive forms, so forms which have co-prime coefficients, are also preserved by the action. So primitiveness is also preserved by the action of SL2. Okay? So now I can get to what I want to define, which are certain equivalence classes of forms. Okay? So for integer b, we define the following sets. First, we simply say, okay, C of D are the classes of forms which have discriminant D. Are the equivalence classes of forms, or binary quadratic forms, of discriminant D. Now, we saw that we can restrict to primitive forms. So we say CP of D, because P for primitive is the intersection of C of D with the equivalence classes of primitive forms. And And then finally, as mentioned, also positive definiteness and indefiniteness is preserved. So what we can say is C plus of D, we will split into two cases. Kind of similar to how the narrow class group is not same for a positive or negative D. We say that it is simply Cp of D if D is bigger than 0, since there is no clear difference between positive and negative in the first case. It's just one structure of indefinite forms. But when D is negative, there is a really clear difference. They are the same thing, just with a minus sign in front of it. So we say that the intersection of Cp of D with the equivalence classes of positive definite forms indicates that D is small. Okay, so this is what I really wanted to get to. We have some similar notion to an equivalence class of ideals. Now we have equivalence classes of quadratic forms. Okay, and now I want to get to the big theorem. Shall I? Yeah, I'll start on the next board. How much time? So now what I want to show to you, or what I will, I really want to get to the, let me just say, I want to show you the correspondence, or actually the bijection between the narrow class group and this group, or this set Cp of D. So showing this theorem requires a lot of work, which I will not be able to do in this talk, but I want to show it to you and really explain the consequences of the applications it has. So we start with an integer D, such that D is 0 or 1, 1, 4. The reason for this is actually because of a discriminant of a quadratic form always has this property. The discriminant always has 0 or is 0 or 1 mod 4. So start with possible discriminant of a quadratic form, and we can write D into a square part and a square free part, simply by taking square powers of primes in its decomposition, grouping them all inside of F, and here we have a square free part with dk squared. You might see where I'm going with this notation, because we can now view dk as a discriminant of quadratic field. So we say that k be the quadratic number field of discriminant dk. And I also wrote F potentially, because we say that and O is the order of conductor F. So now you can see where we are going. I now say the following maps define a bijection narrow class group of this order and the equivalence classes of primitive positive definite forms of discriminant. Okay, what are these maps? So, if we have an ideal class, I write A for an ideal, besides the narrow class group. We can choose a basis for this. In the first part of the handouts, I wrote some more words on this. With a basis alpha beta, then we define the image of this class as the norm of alpha x plus beta y, where x and y are now so variables of the form, divided out by the norm of the ideal. I think I mentioned also what the norm of the ideal is in the handouts. And we take the class of this. This is then an equivalence class of positive definite forms, or indefinite if these be zero. Okay, and conversely, the inverse image, if A, B, C is a class of forms, then say that psi of C is defined as the ideal generated over Z by A and B minus parent of TK over 2 Z. And then we take the class of this inside the narrow class. Okay, now I get that this might seem like a whole lot that I'm giving you here, and I wish I could explain everything more, but the really important part is that there is a bijection between these two sets that I defined, narrow class group, and the sets of equivalence classes. I think if you want to understand it more, I wrote down an example in the handouts, but I really want to get to the consequences this theorem had and what the nice implications of it are, which I specifically like in the context of cryptography. So I hope you can forgive me that I just mentioned the theorem. It's a nice result and, in my opinion, very elegant. But I want to give you some idea of the applications of this bijection. Okay, so the first thing some of you might have noticed is that I keep saying class group, but I am not saying perform class group or anything, because there is no group structure on CP of D. Okay, but now through this bijection, we can actually transport the structure of the class group to the binary quadratic forms. So we can endow CP of D with a group structure. So directly we would do this by saying, okay, suppose we take two classes and define the multiplication simply as what the multiplication inside of the class group, and then I put it back to the binary quadratic forms. This would define a group structure, but you might guess this is not that easy to see what this would be. But luckily, Gauss in 1801 in this really important work, Disquisitiones Arithmeticae, 1801, he actually defined a composition law on binary quadratic forms. But here's the surprising part. Gauss did this without even knowing the notion of a group or an ideal. He just intrinsically found the composition on binary quadratic forms and nice properties it should have, so that it is actually this group structure, which I find really surprising, especially because his composition law is considered to be one of the more deeper and complex results of binary quadratic form theory, and it's really quite hard to understand why it's correct. And that's why also several mathematicians have tried to find a different way to view the Gauss composition, because his composition law, which is the correct one, is referred to as Gauss composition. Okay, So over the years, people have tried to find different perspectives on this, which are more interpretable. And in 2004, Indian mathematician Manju Nagada, who has also won a Fields Medal, developed an entirely new view on the Gauss composition, and using so-called integer cubes, which are now called Algebra cubes. And I won't be able to explain this method here, but what it does is construct some kind of object, in this case a cube, which represents the forms, and then he finds a new way to view the composition of forms. And the nice thing is that he also has found generalizations to higher degree structures. So he also has composition laws for cubic, quartic, and even quintic forms. Which I find really nice, the possibility to generalize this to not just the quadratic case, but higher degree fields. Yeah.
So this, when you say composition law, is a group operation also for these generalizations?
Yeah, also, yes. So that's really the nice part. Because when I'm doing my thesis in the context of cryptography, what the idea was, when the earliest methods were developed, was to use structure of the class group and possibly its added security compared to normal structures, to develop new methods which would add more safety, and we wanted to adapt existing methods like Diffie-Hellman or El-Gamal to class groups. But the problem was that the class group, it's a difficult object to work with. There was no real feasible way to do computations. So what this correspondence does is we can bring over the structure of the class group to something way more computable, binary quadratic forms. For binary quadratic forms, it's way easier to define algorithms, to compute things, to find representatives of the equivalence classes. And so what happens is cryptography on class groups really is supported by this theorem, by the fact that we can work on the quadratic forms for computations, but still have the structure and security of the class group, which I find really interesting in my opinion. And what I find even nicer is that there's possibility for generalizations to cubic and quartic forms, even using the study of Background. And then finally, for the really algebraically minded people, the study of class numbers. Of course, known to be very difficult. So the class number is the size of the class group. Now, when we are working with equivalence classes of quadratic forms, there is a certain thing called a reduced form. And reduced forms will be the representatives of our classes. And actually, through what are called reduction algorithms, one can efficiently compute these reduced representatives and actually find the class number of quadratic number fields very easily. And that's also what I really like. It's like the best of both worlds. You get some good parts of the class group, but you can have the computability of the binary quadratic forms. And yeah, I wanted to share this correspondence with you, even though I might not have gone into real detail. I wanted to explain how this enriches like both the class group and number theory, as well as binary quadratic form theory. Okay, I want to thank you for your attention.